Let's take a look at implicit differentiation with multivariable equations. I'm going to start off with a really simple example. Let's take y equal x squared. Now, from Calc 1, you know that dy dx is 2x. I'm going to show you a pretty fancy way to get that same answer. I'll make it harder. I'm going to make even this simple thing harder. Not really. What I want to do is show you a really sophisticated technique for multivariable equations that I can get the rates of change of any one of the variables with respect to any other variable. It's a really fancy and actually kind of easy method for finding derivatives that I will start with this basic one. So the idea that I will follow is to take whatever equation I have and move everything over onto one side of the equation and create a multivariable function in that way. So I'm going to rewrite this equation as y minus x squared equal to 0. And then I'm going to call this a function of two variables. Once I have that function of two variables now, I can start taking partial derivatives. And so the technique that I'm going to follow is to find the derivative of one variable with respect to the other, as long as I've found this multivariable function equal to a constant. So if you bring everything over one side, you'll have it equal to the constant 0. That's all you need to do to create this f. What you'll do is negative of the partial of f with respect to x over the partial of f with respect to y. The way that I remember this is just since I see an x in the denominator here, I put an x up there. And since I see y on the top, I know that I need y on the bottom. So it basically kind of flips in my mind as to the order in which I put these partials. So what's the partial of f with respect to x? Let's say if you take a derivative of this function f with respect to x, you're going to get just negative 2x, right? Because the y in this derivative is held constant and its derivative is 0. And when I take the partial of f with respect to y, that's just going to give me 1. And so what we do now is say this negative is part of the formula, or part of the technique or method. So that's negative of negative 2x over 1, and there I have the answer that I knew all along, a much easier way. But now we've got a really powerful tool. I'm going to try to make this a quicker video so that we're just doing the applications of this principle. It's called the implicit function theorem, and proof of this would be really an interesting thing to do, but I'm going to just focus on getting some examples in this video. So let's go on to another one. Let's move on to another example. X cubed times y plus y cubed minus 4xy equal y to the fourth. And let's do this, let's find dy dx, and we'll do it two different ways. We'll do the Calc 1 method using ordinary derivatives, and we'll use a Calc 3 method that uses partial derivatives, and it's that Calc 3 method that will allow us to handle finding derivatives with any number of variables. Well, let's do the Calc 1 method first. How would you do this if you're in Calc 1? Just as a reminder, so if we were doing this the Calc 1 way, we would take a derivative of both sides with respect to x because we want to find a rate of change of y with respect to x. So this is the operator taking a derivative with respect to x, the differentiation operator. So here I am writing derivative with respect to x on both sides of the equation. We'll go through each side and differentiate with respect to x. So this will require product rule. Moving on to this term, taking a derivative with respect to x, and since this is y, a different variable, we'll use the chain rule. What I could do here is to treat the minus 4 as a constant and then apply product rule to this product here. So the derivative of x with respect to x is just 1. We get 1 times y plus now x times the derivative of y with respect to x. And now here, on the right-hand side of the equation, a derivative with respect to x of y to the fourth Well, we've got to use the chain rule because we're taking a derivative of y to the fourth power with respect to x. So 4 comes down, y to the power 3, I've subtracted 1, and then it's by the chain rule that I write this factor of dy dx, the derivative of y with respect to x. Now from here what we're going to do is just move all the terms that have dy dx onto one side, on the left side, and then isolate dy dx by factoring it out. So right there I distributed the negative. And now I'm going to write all the terms with dy dx on one side, on the left-hand side. Make sure I get all the terms. And switch signs when they move from one side to the other. Factor out dy dx. And divide by that expression on the left-hand side, and that's it. Let's take the same equation, let's find dy dx, but let's use the Calc 3 partial derivatives method. Now in our book, this is called we're going to use what's called the implicit function theorem, which I'm not going to try to prove in this video, I just want to do some examples of applying that theorem. And actually, I don't really need this method to do this particular equation, and that was the point of why I just did the previous, I did it in the previous example. But what I want to demonstrate here is this method that would generalize to any number of variables, and that's why it's important for the Calc 3 classes, that we can have any number of variables and find the rate of change of any variable with respect to any other variable in that equation, which is pretty impressive. So the first thing that we need to do in this method is to bring everything over to one side of the equation so that we have a new function of all of the variables involved equal to a constant. So rewrite it like this. Identify this as a function of all of the variables involved in the equation. And now you can find the derivative of any one of those variables with respect to another. I'm still using normal d's here because this is ordinary derivative here, y depending on only x. And so our method is to say partial of f with respect to x divided by partial of f with respect to y. So let's see if we can just do that. This will make it look like this is an easier method than what we just saw doing it the other way. Let's see, if I take a derivative with respect to x, I'll get 3x squared y, because y is a constant right now. And this will go to 0, and then I'll have, taking a derivative with respect to x, I'll just get minus 4y. Yeah, and don't forget, there's a negative here. That negative right there in the front, so easy to forget. So I almost did it. So there it is. Derivative with respect to x times the constant y plus 0. And then a derivative of this term with respect to x. And then this last term, taking a derivative with respect to x, this is all constant right now in the derivative with respect to x. In the denominator, a derivative with respect to y. So the x cubed is a constant. This will give me 3y squared. A derivative with respect to y here gives me minus 4x. And then the derivative with respect to y here just gives me minus 4y cubed. And then just to check back that that's the same answer. Yeah, that's the same answer that I got the other way. And boy, that really did look a lot easier doing it this way. So that's a good thing about this. It's a pretty easy method. It can handle any number of variables. And I just solved one that just took a whole page really pretty quickly here. All right, moving on to another example. Let's just expand a little bit in the number of variables. So I want to find now, you see I have 3 variables, x and v and theta, and let's just say, how about we want to know the rate of change of v with respect to theta, And now I'm using a partial derivative notation because v may depend on more than just, in fact it does here, changing x and changing theta would change the values of v that would satisfy this equation. So v, in a sense, just in a purely abstract algebraic sense, depends on both x and theta. So to find the rate of change of any variable with respect to any other variable in any equation, what we could do is take the entire equation and rewrite it so that it's equal to a constant, and then use that function capital F to do partials of that function. So we'll write it as this. So now I've created this capital F function that depends on x and v and theta, and if I want to find the derivative of v with respect to theta, a derivative of f with respect to theta for this function, big F, taking a derivative with respect to theta, x is going to be a constant. The 1 over 9.8 v squared is all constant right now if the variable with which I'm differentiating is only theta. So this term will go to 0 because it's a constant term, but this is a constant factor times the function of theta. So this constant factor gets copied in the derivative. So first of all, I had to copy the negative from the formula, and then I copy a negative 1 over 9.8 v squared as a constant factor times the derivative of sine 2 theta with respect to theta is cos 2 theta, and then a chain rule factor that gives me this 2. Taking a derivative now of this whole function capital F with respect to v, once again this term x is a constant, doesn't change if I'm taking derivative with respect to only v of this function f. Right there. So the derivative with respect to v, that's going to be 0. Derivative with respect to v here, the 1 over 9.8 and the sine 2 theta, these guys are constant right now. And the v squared, I get a derivative, the 2 comes down. So we'll get negative because there's a negative here. Let's say 1 over 9.8, then 2 times v times, and then this sine 2 theta is just a constant factor. So I've got 3 negatives here, so only 1 left over. And actually, though, we could even just say this 1 over 9.8 is going to cancel, and the 2's cancel. Let's just do it like that. So I've got negative v squared cos 2 theta over single factor of v sine 2 theta. So that's that one. Okay, let's move on to one last example of this kind of method where we can find derivatives of any variable with respect to any other variable in any equation with any number of variables. It's fun to be able to say that. All right, well, the thing that starts this whole thing is that you've got to move every term and everything all into one side to create this capital F. Right, so we had an equation that has 3 variables, and it's really inconvenient to solve for any one of those variables. Right? So that's why we need this method, and why this is so useful, is to be able to find rates of change without trying to solve for any particular variable. Right? I can still find the rate of change of y with respect to z, or z with respect to x, or x with respect to y, or anything, without trying to do the algebra of solving for any one of those variables. So it's really convenient. So then what you do is you say, okay, let's create this function capital F. This is a function of 3 variables. And if I want the derivative of y with respect to z, then I'll do minus partial of f with respect to z divided by partial of f with respect to y. And I'll fill that in a minute, and I don't want to forget the negative. So let's see how that goes here. I need to take the partial of f with respect to z, and don't forget the negative, so maybe just put that down before I do anything else. Taking a derivative with respect to z, well, this whole term turns out to be just 0 right now because it involves no factors of z. When I get to this guy, I've got two factors involving z, and I can't multiply them together, so I'm going to have to go with product rule. So let's say I might just consider there's a negative that I need to track through the product rule, because in the derivative of this whole thing, that negative is going to apply to all of the terms that come in the derivative of this product. So there's another negative. Derivative with respect to z of this by the product rule. Actually, the derivative of z, that's just going to be 1. So really there's a 1 arc sine xz plus now z times the derivative of the arc sine of xz, where x is a constant. So the derivative of arc sine is 1 over a square root of 1 minus the argument of the arc sine squared. And then by the chain rule, we would get a derivative of the argument with respect to z, which means I get an extra factor of x because it's a constant factor times the expression or the variable z. All right, so that looks good. Now let's take a derivative of this function f with respect to y. Again, I'm going to use product rule here, and I won't really need quotient rule for this thing because the numerator is a constant right now when I take a derivative with respect to y. So let's go product rule where we've got, let's say, negative x squared y to the negative 2, right? Because this guy is really y to the minus 1. So having a minus 1 goes down in front. That's what that guy is. X squared is a constant. This is y to the minus 2 because I had to subtract 1. And then I get e to the xy as the other factor of my product rule. This is a u and a v. And u prime is here, and that's v. Now plus, then I'll get this x squared over y because of the product rule, times the derivative of e to the xy with respect to y. So continuing my derivative here, I've got this x squared over y factor that is the first part of my product rule. I'm doing the derivative of e to the xy with respect to y. So the derivative of the exponential is equal to itself times any chain rule factor. And the chain rule factor is going to be an x because I'm taking a derivative with respect to y now. And the x is a constant factor in that argument. So I get this extra factor from the chain rule. Oh yeah, and as we continue taking the derivative with respect to y of this function f, there are no factors or terms involving y in the rest of the equation. So all of this is constant with respect to changes in y. Because it doesn't involve y, it doesn't have any change with respect to y because it's simply constant when the only thing that's changing is y. Okay, so that's the denominator worked out. So let's just see if we can clean this up a little bit. This negative was actually for everything in the numerator. I am missing a parenthesis here. But since that negative was applied to everything in the product rule, which was everything in the numerator, that negative can cancel with that negative, and we're left with arc sine xz plus the xz factors divided by the square root of 1 minus, let's say, x squared z squared. And then here I've got an x squared times an x gives me an x cubed. Now what I have here is a fraction that contains fractions, so that's not simplified. So let's do one more step here and simplify this complex fraction. So we'll multiply the top and the bottom by the common denominator of all the fractions. here the square roots canceled, and I'm just left with these factors of x, z, and y squared. And I put them in alphabetical order, which is a sort of typical thing to do. Now when I distribute this factor times both terms, the y squared cancels, and then the one factor of y cancels when I distribute here. Alright, so let's leave it at that. I mean, it's typical that in a derivative you want to factor it, but I don't see much really helping. I mean, we could factor out a y squared on the top, and we could have factored out that e to the xy square root, but that doesn't seem worth it in this example. So we'll stop there with that one, and we got one more. So go back to the equation. We're looking for dz by dx, and we need to have this written in the correct way. So to find the derivative of z with respect to x, I'll do the partial of f with respect to x and the partial of f with respect to z, divide them and include that negative. Partial of f with respect to x, well, we're going to get the y is a constant right now, so let's just go. So taking a derivative with respect to x, I notice that I've got two factors that both contain an x, so I do need to keep track of the product rule here. So a derivative of the x squared over y with respect to x is going to be 2x times the 1 over y factor times the e to the xy that's just there as the second part of the product rule, plus now the x squared over y, that's the first part of the product rule, times the derivative of e to the xy with respect to x. And now the derivative of this xy product with respect to x gives me this extra factor of y. Now moving on, I notice that there is an x buried in here, which means I need to take a derivative of this with respect to x, treating the z to be constant. I'm running out of little space a little bit here. Alright, so a derivative of this with respect to x is going to have a negative z, because it's a constant factor. The derivative of arc sine, and then a factor by the chain rule in the differentiation with respect to x is going to give me an extra z. Now I'm dividing by the derivative with respect to z, which I can look back on the page I just did to copy it. It's going to be exactly the same. Or I think what I'll do is run through it again and then look back to make sure it's the same things as another chance to check any or catch any errors. So taking a derivative with respect to z, not so bad. See, this is all going to go to 0. So a derivative with respect to z, it is product rule. It's going to give me negative arc sine, because the derivative of with respect to z is going to be a negative 1 times this factor, arc sine xz. So easy to mess up with all these signs, so let's do it like this. We'll do a negative and then do the product rule, just because it's so easy to mess up. Do a little extra care to avoid errors. So just in the product rule, I'm bringing the negative out so I don't have to think about it. Then I'll just do the product rule, a derivative with respect to z. So we'll get a 1 times arc sine xz and then plus the z, and then a derivative of this arc sine with respect to z is 1 over square root and then times an x by the chain rule. Now that's a negative and a negative. Both of them are going to cancel. let's say we can cancel this y with this y. And now we've got two factors of z. The negative is gone. Okay, and checking with the work that I had done on the previous one to get that partial with respect to z, this looks okay. And once again, I have a fraction that contains fractions. Oh, there's a factor of y here. And then distributing in the denominator. Okay, so there it is. Yeah, I know, that was crazy complicated, but I wanted to show that it could be done, and I wanted to do one that was sufficiently complicated to handle the sorts of different things that could happen on an exam. All right, hopefully that was helpful. I think I'm going to definitely stop here for now. Okay, I thought of one other thing that I'll just tack in, one other idea that's, as far as the sort of way that you do this, maybe it's rather than following what I did here, if you write out each of the partials first and just focus on that might actually help, because then you could do each of the answers. If you had to find the derivative of z with respect to y, for example, then you could go right into just copying down the work that you did. So I think you're better off if you break it up into two different things. Getting all of the partial derivatives first and focusing on just that, and then moving on to applying those partial derivatives to find a particular other derivative from the original equation, right? So you don't mix up the fraction and which one you're supposed to do, and obviously the negative is easy to mess up. Do all the partials first, then plug it into this formula. I think that's a better strategy.